This object here has a speed of, right there, 100 meters per second. And I'm going to turn gravity actually off. There we go. And I shoot it to the right. And I try to stop it as close as possible to 1 second. There it is. Okay, it didn't quite make it. After 1.073 seconds, starting over here at 0, it has reached just past 100 meters. I did post the actual distance it covered, 107.250 meters, and we can see that therefore it covered 100 meters per second. Okay, so let's start over. This time I'm going to turn gravity on. There we go. I'm going to do the same thing. Of course, now it's going to fall. And again, I'm going to try to stop it right next to 1 second. Let's see. Okay, a little bit more. 1.105 seconds. We see it's around 110 meters here. So 110.5 meters in 1.105 seconds means it still goes 100 meters per second. So no matter if gravity's turned on or if it's turned off, in the horizontal, that object will go 100 meters after 1 second. Okay, again I'm going to reset. This time I'm going to shoot it straight up, and once again I will turn gravity off. I'm going to put it at the 0 mark here, and I'm going to double check if I just changed that, yep, to exactly 100 meters per second. And as I said, I will turn gravity off. There we go. And I'm going to shoot it again close to 1 second. Okay, a little bit short. I don't think I'll make it exactly. Oh, there, just a little bit more. Okay, so at 1.109 seconds, it has gone up 110.95 meters, which means without gravity, we can compare these two numbers, it makes 100 meters per second. Now I'm going to turn gravity on. Reset, turn gravity on. Now at the same time that it's going to go up 100 meters, it will also fall a certain distance due to gravity. In fact, if this object here has no speed at all, and so it's just going to fall under the influence of gravity. Here we go. After 1 second, oh, that was as close as I possibly could get, negative 6.350 meters. I'm going to try it again. Okay, I'm sure that's how close I can get. So negative 4.416 meters after 0.949 seconds, to show here that it has actually, that it would fall 4.9 meters, which is 1/2 times 9.8 times 1 second squared. It's just too tough for me, and respectively, it's tough to see that indeed is the case. In any case, though, I have to click on the object and put it back at a speed of 100 meters per second. In any case, as it's going up at a speed of 100 meters per second and falling down at the same time, trying to fall down, gravity trying to pull it down by those 4.9 meters after 1 second, however, before I click the run button, I have to slow this applet down, the software, make this more accurate. That means that the time is much slower now, because I need to really hit it on 1 second, or as close as I possibly can get. So here we go. Notice that it's a whole lot slower because I did slow it down. And I try to hit the stop button at just 1 second. Let's see if I can do that. Okay, try getting a little closer. Okay, I don't think I get it any better. Notice that it went up 0.979 seconds, but it didn't make 97.9 meters, as if it was going 100 meters per second, because gravity slowed it down. So it's a little bit less. Let's see if I can get even closer. I don't know. Yep, see now it's at 1.024 seconds. It's still not at 100 meters because gravity slowed it down. I'm going to try it one more time. Earlier in my trial run, I did actually come up with 0.999 seconds, and it pretty much was on the 95 meter mark. So let's see. So going up at 100 meters per second originally, but gravity already had slowed it down. Okay. Yeah, I don't think I get any better than that. So after 1.013 seconds, it has only made 96.304 meters because it cannot make 100 meters anymore because gravity is starting to pull it down as soon as it went up. This 4-meter long board is sitting on a fulcrum, which sits on a table. Notice these anchors here. That means that neither one of these here is going to fall down as gravity is acting in the entire screen here. So when I just push the run button and the object falls down, the board, because it's not center, is going to tip, but because of the anchors here, the fulcrum and the table are just going to stay there. Okay. Now if I take this board here and I carefully set it on top of the fulcrum of its center, the object of course is still going to fall, but the board is balanced now because its center of mass is right above the fulcrum. Notice over here the position of the center of mass of the board is at 3 meters. That's because I shifted the board over here, so the center of mass is right here in the middle of the board, right above the fulcrum. I'm going to shift it back. Now, of course, the center of mass is still the middle of the board, which of course is at the 2 meter mark, 1 meter away from the fulcrum. The board is gravity is exerting torques on every piece of the board over here, 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 everywhere, 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 everywhere. However, in order to calculate the total torque across the board would take a calculus problem to do so. Respectively, one could look at, on the left hand side there would be a torque pulling it this way. On the right hand side there would be a torque pulling it this way, but because there is more material of the board on the left hand side, we would expect a net torque to pull it this way here in a counterclockwise fashion. Of course, that's exactly what the board is doing. In order to avoid calculus, we just say that, well, the net torque is actually right here along the center of mass of the board, and that is at this point here 1 meter away from the fulcrum. It would be wrong to say that there would be a net torque on this end and a net torque on this end, respectively, that all the mass of the board is over here and all the mass of the board is over here. It's just that in order to avoid that entire calculus problem here, as I mentioned, just think of the mass concentrated here, and this is where the net torque is pulling on the board. Okay, let's set the object on top of the end of the board. And I might have mentioned this earlier that we actually don't know the mass of the board. We're going to try to figure it out. Here's the object, and apparently has a mass of 0.283 kilograms. So let's see what's going to happen. And indeed, the object apparently doesn't have enough mass, doesn't have enough weight to counteract the torque of the board. So the board is still going to tip. So we're going to increase the mass of the board, let's say 0.283, double that. Let's just make it 0.5 rounded here. There we go. Hit the run button, and the object here, the ball, is still not massive enough. It still doesn't have enough weight in order to produce a torque that is counteracting the board's torque. So I'm going to double it again, 1 kilogram. Okay, this time it's the other way around. So now the object actually has too much mass. So I'm going to take something in the middle, 0.75 kilograms. Okay, not as drastic, but the object is still not massive enough. So again, I'm going to go somewhere in the middle here, 0.9 maybe. Now it's too heavy again. Okay. So Let's try 0.85. Okay, still too heavy. Let's try 0.8. And still rolls off here. Oh, yeah, this time the board was too heavy, so I'm going to try 0.81. Okay, still rolls off. Okay, it pretty much sits there. Okay. So, the object of mass 0.82 kilogram exerts a torque right here at the end of the board, while the board, and that is 1 meter away from the fulcrum, while the board essentially exerts a torque right here along its center of mass, which is also 1 meter away from the fulcrum. So in order to have the same torque here and to have the same torque here that balance each other, at a 1 meter lever arm for the object times gravity 9.2 times the mass of the object 0.82 kilograms, that needs to be the same as the lever arm over here, which is also 1 meter, times 9.8 times the mass of the board. And because to the left and the right the lever arms are the same, the gravity of course is the same, so therefore the mass of the board has to be the same of the object, which is 0.82 kilograms. Oh yeah, I have to reset this here. 0.82 kilograms of the object. There it is again. So let's see what the board has. 0.80 kilograms. Essentially the same. It's just a little bit off because I wasn't able to place the object exactly at the end, because I think otherwise it would have really rolled off at all times. So I just placed it just a little bit in that requires a little bit more mass here. But overall, within measurement error, the board has the same mass as the object because its center of mass is also 1 meter away from the fulcrum, as is the object. Alright, let's change the situation. We make a 6 meter board instead. And I'm going to see this time around, okay, 1.2 kilograms. Let's assume that we don't know the mass of the board, even though I just checked it a moment ago. I'm going to place the object here and let it run. Obviously totally upset. Okay, let's double that. 1.6 kilograms. Okay, not enough. Let's double that again. 3.2. This time this one is too much. Okay. Try something in the middle. 2,400 maybe, 2.4. And oh, just got off there just a little bit, so maybe a little bit less. Okay, still rolling off a little bit. But I think that's because I'm not exactly able to place it at the exact end. So I'm going to try. Yeah, I don't think I get it any better. Let's see what it says here. Yeah, it just doesn't get any better. I'm going to go back to the 2.4 I had here a moment ago. At least for a moment it was stable. Yeah, and then it upsets itself. But just at least for that one moment it was stable. And again, that's because it actually tries to roll off, since after all it's round. Okay, what do we have here? We have a 1 meter distance for the object. So 2.4 kilograms times 1 meter lever arm times 9.8 for gravity. And for the board, we have the center of mass of the board, which now is 2 meters away from the fulcrum, times the mass of the board times 9.8. 9.8 is the same on both sides. Here the lever arm is twice as long, 2 meters. Here it's only 1 meter. And that means that the mass ratio, as the lever ratio is 2 to 1, the mass ratio needs to be 1 to 2. So the 2.4 kilograms here is twice as much as that of the board. That should be 1.2 kilograms, and of course we saw that earlier, it is 1.2 kilograms. And just for a moment, it is actually stable until the ball actually does roll off, since after all it's round. So here I got a broomstick and the brush part, and actually these are two different pieces in the software that I just joined together right here, and then I'm going to put it on a fulcrum. Actually, this is kind of cool. If I just drop it, there you go, it actually sits perfectly on the fulcrum. There you go, totally balanced. So that means that the torque on the left equals the torque on the right. Let's just do it a little bit different. Let's push the broomstick over here a little bit, and what's going to happen? The whole thing is totally upset. And then unfortunately the whole thing actually, whoa, just turned on me. So what about if I do it this way here? It does the same thing, totally upset. So I do have to put it right there at their combined center of mass, and now the thing is balanced right there at that joint. Okay, now I'm going to take the joint away in a moment, but let's look at it. So here I have the broomstick. Its own center of mass is apparently over here. So this one here has a relatively large lever arm, and the brush part's center of mass is here, so this one here has a relatively small lever arm. So in order to produce the same torque on the right hand side and on the left hand side, the broomstick must have less mass at this about 2.5 meter lever arm here, really big broom, I guess, while the brush part over here with a lever arm, essential lever arm of about 0.8 meters maybe, must have relatively small mass in order to produce the same torque. Okay, so let's take it apart. I'm going to take off that joint here. So here's the broomstick. It has a mass of 0.5 kilograms, while the brush part has a mass of 1.4 kilograms, almost 3 times as much, just as the lever arm for the broomstick was almost 3 times as much as the lever arm for the brush. So when I saw this broom apart into two pieces, no, they're not of equal mass. The broomstick has less mass due to its long lever arm, producing the same torque if I try to balance it on this fulcrum here, together with the brush part, whose larger mass is closer to the fulcrum.